Hello everyone, I'm Fatima Hanani and I'm a doctoral student at the Last Semi Laboratory at Mohammedia Engineering School. And today I will present you my paper entitled Fuzzy Logic Framework for the Assessment of Local Accessibility Based on Built Environment Characteristics, written by myself, Hanani Fatima, and Soulhi Aziz. In this regard, after introducing my work and explaining the problematic, I will expose the research context and method, followed by the result that I have obtained. And finally, I will end my presentation with the contribution of framework and the conclusion. First, to introduce in both scientific and professional community the need to integrate transport and the land use policies in order to achieve more sustainable urban development is widely recognized. Accessibility can provide a conceptual focus for this integration because it is related both future of transport system and as well the land use system. Besides, accessibility has recently gained ground in city institutions that can use it most effectively as a planning tool and also as a tool for evaluating the effectiveness of policies for land use and transport planning. Despite a substantial amount of research on building environment and transportation, there have been limited studies on the importance of built environment characteristics in terms of accessibility. Moreover, in order to identify effective strategies for increasing sustainable and active mode of transportation in local areas, planners need to identify how land use planning in neighborhoods affects accessibility. Hence, in this paper employs new approach for measuring accessibility against land use futures. To begin with, according to the accessibility literature, there are three methods of measuring accessibility that are cumulative opportunities, gravity-based measures, utility-based measures. These accessibility measurement methods present several issues and limitations, namely the lack of understanding of accessibility concepts among politicians, the politic and non-modelers, technical and computational complexity, lack of standardized software availability and the data, imprecision that concern variables and intervals for the first method. Therefore, all methods presented above calculate accessibility as a function of transport system parameters like cost, travel time, and distance. This is why the aim of this work is to highlight the fact that accessibility is also an outcome of the urban design. Thus, we present a new method based on fuzzy logic to assess the accessibility according to the urban characteristics of the area that we will call built environment-based accessibility measure. One may wonder why the use of fuzzy logic. In fact, it is difficult to set up a measure of accessibility with the precise variables and intervals. Besides, city managers need to read, understand, and easily modify the rules of accessibility calculation model. Moreover, with fuzzy logic, the accessibility measure is easy to understand and interpret thanks to use of linguistic variables and human reasoning. To measure the impact of land use on travel behavior, 5 characteristics are studied, also called 5D variables, standing for density, diversity, design, destination accessibility, distance to transport. For our study, we chose to limit our research to the three first considered by the scientific literature to be the key factors that most influence active transportation modes. After presenting the variables, we now focus on fuzzy logic methods. This approach attempts to simulate human reasoning and allows integration of imperfect data in a decision process. The basic characteristics of fuzzy logic are linguistic variables, universe of discourse, function of membership, and fuzzy subset. Moreover, the operating principle of fuzzy logic system includes 3 phases: fuzzification, fuzzy inference engine, and defuzzification. First step, fuzzification. To model our system to evaluate local accessibility, we have to define 3 input variables and 1 output. As shown in this table, for each variable, there is a formula, the fuzzy subset, and the membership function. These variables are activity density index, ADI, land use mix, LUM, street design and connectivity, represented by PRD, local accessibility index, LIE. Fuzzy inference. The second fuzzy step is fuzzy inference. In this step is where human reasoning will be applied. This phase consists of 2 steps. The first one is to build decision rules and to find for each of them the membership rule of the conclusion. The second one consists of the aggregation of the conclusions. For this step, we use the Mamdani inference mechanism. As you can see here is an example of rules from our fuzzy inference system. Finally, we can evaluate the local accessibility through our fuzzy system. It is the defuzzification step. To study the relation between our input variables and the local accessibility, we will proceed to the analysis of the surface graphs for 3 cases. Cases 1, ADA in an average value. In this case, we set the density to an average value and we see how our system reacts. We can see in the figure that when the density is medium, we can only expect the medium value of accessibility. Therefore, when the PRD is low, accessibility remains low, whatever the value of LUM variable. This supports the fact that the ease of access is an important component to consider when studying and planning local accessibility. Case 2, we fix LUM in average value. As we can see in this figure, when we set LUM to a medium value, we notice that this case presents the same result as the previous one. From case 1 and case 2, we conclude that land use mix has the same impact on local accessibility as the density of activity. Case 3, we fix pre-RD in average value. As we can see in the figure, in contrast to the 2 previous cases, the most important remark is that accessibility can reach high values, but with one important condition. Both ADI and LUM must be high. In addition, this graph shows 2 main findings. Local accessibility can be medium when at least one of the 2 variables has a medium value. And the second, local accessibility is low when at least one of the 2 has a low value. This result is consistent because when the density is low, there is no reason to talk about the land use mix. Moreover, when the density is high and the land use mix is low, we conclude that the area presents only one activity. In both cases, the accessibility remains low, except when PRD becomes high. In this case, accessibility becomes medium. Furthermore, we can also conclude that combination of ADI and LUM characteristics are more important and relevant to achieve a high local accessibility. As a contribution of our work, we can say that our method allowed us to extend the scope of cumulative opportunity method by considering the surrounding land use environment. Also, it's allowed to evaluate local accessibility using the principle of gravity method, incorporating an impedance function, capturing the access condition to each opportunity by PRD. In addition, it considers the two main components of accessibility, which are the ease to walk or cycle to reach destination, and the quantity and spatial distribution of opportunities. The first component is represented in our model by the characteristics street design and connectivity, PRD, and the second is represented by the combination of the two other urban characteristics, activity density index and the land use mix index. This model presents a high level of disaggregation to capture small-scale design future streets and to also evaluate no motorized trips, and therefore allows helping city decision makers predict the full impacts of land use management strategies on improving local accessibility, such as densification of activity, mixing activity, and bringing them closer together by improving walking and cycling conditions and pedestrian-friendly environments. Obviously, for a model to be relevant and effective, it must be exhaustive and consider all the factors and elements that can influence accessibility. Even though our model tried to consider the two main components of accessibility, we could not consider how these two components are perceived and used by individuals with different characteristics. Therefore, our model has only dealt with one part of accessibility in the city, which is the local accessibility that concerns only the active modes of transport, and it has not considered the regional accessibility and the other modes of transport. To conclude, it is widely known that accessibility is a major effect of the transport system. However, this paper shows that accessibility is also a matter of urban planning. In particular, we have found that local accessibility can be defined by three urban characteristics: activity density, land use mix, and street design. In the perspectives, and to complete this work, our model can be extended to treat the question of accessibility in a global way and to consider the regional dimension. Also, our work can be improved by testing it with the real data to better calibrate it. Thank you.